So now that we have explained why we need limit, we're gonna move on to the mechanics of using limit, and that's limit laws, which is chapter 1.6 in our textbook. The most important rule that you need to remember is for polynomials and rational functions, you can directly the limit is simply the value the function takes on. So that's called a direct substitution rule. The limit of fx as x approach a is fa. That's something that's very reasonable if you think about the diagram. This is what a polynomial looks like. This would be a very high order polynomial given how it's moving around, but the diagram is kind of how a polynomial is, right? If it's x is just a straight line, if it's x squared is a quadratic equation, x cubed then it goes up and down and so on, right? So a quadratic equation simply is simply a curve that's going up and down. And in particular, a polynomial does not have any breaks, right? A polynomial is a continuous, graphically, polynomial is a continuous curve going up and down, but it's joined together. There's no step, there's no break that you can anywhere. So naturally, if you think about the diagram for a polynomial, the limit of the function as x approach a would be fa. The function is joined together after all, so it always moves towards that point. That makes it easier for us to use limit because that means that you simply substitute the value in most cases. In economics, we very often just deal with polynomials and rational functions. What cases you would not be able to directly use this rule? The cases that you cannot directly use this rule would be, as you can imagine, most cases where you have fx equals to some sort of conditional function where you have fx equals to something if something is true, fx equals to something else and something else is true, that you have to be careful because that would very likely imply there's some sort of a break somewhere, right? And you have to be extra careful in that. But if for most cases, especially in the assignment, it would just be polynomials and it's going to be easy. So what do you do with polynomials, as we say, simple, just substitute the value in. But what if you have combinations of polynomials, like polynomials multiplied by a polynomial divided by a polynomial? What do you do? For that, you need the limit laws, which are properties of limits. So let's say you have a constant number c and you have two functions f and g. They both have limits, exist at a certain point a. Then the limit law says that if you're trying to find the limit of the two functions added together, that's the same as the limit of each function added together. So you can break apart the brackets and just apply the limit to each individual function. If you have a function multiplied by a constant amount, you can take out the constant amount to outside the limit, and that would be equal. If you have two functions multiplied together, and then you want to find the limit of that, you can multiply the individual limits. So far, all these just say that you can directly apply the limit to each individual item as you need. The last case is the case where you have to be a bit careful. The limit of one function divided by the other equals to the division between the two individual limits, as long as the denominator is not 0. Because if the denominator is 0, then you have a case of undefined. As long as the denominator is not 0, then you can just, once again, distribute the limit to each individual function. The rules are quite simple, really. We first illustrate graphically why it should be true And then we also have a few more numerical examples following. So first, graphically, let's say fx is 2 and fx is x and gx is 2. Find the limit of fx plus gx. If you look at the diagram, so the blue line is fx, the green line is gx, you add them together, that's a red line. And you can pick any point A. I just picked an arbitrary point here, but you can pick any you want. It's quite clear that the limit of the sum of the two functions would be the sum of the limits of each individual function, right? It's quite clear. The trend of the red line is the sum of the trends of the blue line and the green line. That intuition is expressed in the application of limit laws. You don't need to say that you're using limit laws. You just use them, right? As long as you do it correctly, that's okay. So what you do is simply you directly apply the limit laws. So you break apart the bracket, apply limit to each individual function, and well, what would that be? Here's the part where you can now use the direct substitution rule. Because fx is x, which is a polynomial, gx equals to 2, you can actually say that as a polynomial, right? It's just a constant term, right? So this would be a and 2. So for illustration purpose, I would write down that it's by direct substitution rule, but in the exam you don't need to do that. You just use it. Right, this is by direct substitution rule, and this is by limit addition rule, right? But as I said, in the exam, you don't need to explain. Just use it. Just use the rules. Okay. So that's it for the addition. It's quite simple. Okay. So that's addition. Multiplication. Once again, you have the diagrams, and if you express the multiplication as a red line, then it's going to be going up faster than the blue line because we have twice the slope as before, and it's once again quite clear that the trend of the function as you get close to a is the multiplication of the trend of the two underlying functions, right? So once again, you can use the limit laws. You can break apart the bracket, multiply the individual function. Once again, this is by limit multiplication rule. Multiplication law is called limit laws. By limit multiplication law, and that would equal to, once again, by direct substitution, a times 2, so 2a. Simple. There's really not much there in limit laws. The only case you have to be careful about is if you happen to have division by 0 or infinity. Those are cases you have to be careful. But these in here we don't have that, so it's okay. So the final case is diffusion. So you have x divided by 2, so that's x over 2. It's a flatter line, and it's quite clear that the trend, what the function is moving towards around a is equals to what the function f is moving towards divided by what the function g is moving towards. And in limit laws, you can express that as the limit of f divided by limit of g. Since, now this is the part, it's important because you have to justify that why you can do that. It only works if you're not dividing by 0. And we have to justify that, that's not a lot of space. Let me write it here. Since the limit of g does not, well, it's always going to be 2 and it's not going to be 0, right? So you don't have the problem of dividing by 0. It's always 2, it's never 0. Which means by direct substitution, you have a divided by 2. And that's the answer. That's the limit. Okay? So these cases are easy because you don't have the problem of diffusion by 0 or diffusion, or you don't have any, nor do you have any infinity. So that's easy. Right. So in the assignment, you will see a lot of cases like these. You have polynomial divided by polynomials, right? What do? Well, you just do what we just did in the previous slide. You can split it into. So what you want to do, you can probably start with this, right? So x plus 1 is a polynomial. You can use direct substitution rule, and it's equals to 4. Once again, I'm just going to state that I'm using direct substitution rule, but you don't need to do that in the exam. You do that, that's okay, but you don't need to. So it's not equal to 0, right? So limit Sx of this x squared minus 4x plus 2 divided by x plus 1 as x approach 3 would equal the limit of x approach 3 of x minus 4x plus 2 divided by limit x approach 3 x plus 1. This is so by limit diffusion law, right? So once again, direct substitute. This is a polynomial because these are all polynomials now, so you can use direct substitution. So that's 3 squared minus 4 times 3 plus 2 divided by 3 plus 1, which would equal 9 minus 12 plus 2, that's 1, right? Over 4. That's the answer. Yeah. Okay, so it's very simple. There's really nothing to it. There's a lot of these exercises in the yeah. Yeah. Did I do math incorrectly? 9. Did I do it incorrectly? That's it. You can never trust my math. Okay. Is it? Nine minus 4, 3. What do you say it should be? Is it negative? That's it. You're right. Yes. Yeah. 9 minus 12 plus 2 is -1. Well, that's why you should always trust your calculator. Finally, one more case. This case is a case that you have to be careful about because this case, you actually, well, have a case of 0. So, all right, by direct substitution rule, you have 0. So you can't use the limit division law since you have a division of 0 problem. So what do? Well, in this case, there is a way out because, so can't use limit division law. So what do? Well, fortunately, in this case, you actually have a way out because x squared minus 1, as you know, can be factorized into x minus 1, x plus 1. So now the question is, can you cancel out these two? Note that you cannot cancel out these two terms if x equals to 1, right? If x equals to 1, x minus 1 is 0, and so you have 0 divided by 0. You can't cancel out 0 and 0. That's invalid. You can cancel x. So x over x equals 1 if x is not 0. X over x is not 1 if you have x equals 0, right? So can you do this? Not if x is 1. But right now, what we have here is not x equals to 1. We have x approaching 1, which means x is not 1. X is just very close to 1. So you can't cancel. So this is an important distinction. You can't cancel. So you can't cancel if x equals 1 because you would have 0 divided by 0. But what we have is x very close to 1. So it's okay. So this is the important distinction. If x is actually 1, you can't cancel out. But what we have here is x is very close to 1, which is to say x is not 1. And you can cancel. So we have the limit of x approach 1 of x plus 1 is 2. Okay, so limit help us to figure out what the value of this function is, right? With some so it approaches 2. If you draw a diagram, then it's quite clear. This is the case. We are kind of lucky in this case because we can do algebraic manipulation to cancel out the common term to get ourselves out of this problem. In other cases, you might not be able to do this sort of arrangement. What do? Well, after we learn differentiation, then we actually have a particular method to deal with this problem. We can use differentiation to change our limit into another limit that we change our limit into another limit that would have the same limit. Okay, it's kind of like, you get what I mean. What I guess I should say is, when after we learn differentiation, when we face with a situation like that where we have zero divided by zero, and we can't get away by using algebraic manipulation, there is going to be a rule where we use differentiation to change these two functions into some other functions, and the limit of this limit is going to be equal to the limit of the division of the two other functions. So that's called the L'Hopital's rule. But it's kind of like circular. You have to learn limit to learn differentiation, but you need differentiation to use this L'Hopital's rule of limit. So it comes back again in the future, right? But you have to be very careful in such a case. In our course, I think we're not going to have any case where you can't simplify it algebraically, because we might not be able to get to L'Hopital's rule in the end. So we can't, and I have to write the exam this week. So you're not going to see that. In the exam, you're only going to see cases where you can actually simplify it if necessary. But you have to check, because if you do not check and you directly use the limit division law, that would be incorrect answer. Okay? So you do have to check in case of division. All right. So finally, I think I'm just going to have to illustrate this concept, is that if you have one function always smaller than the other, then the limit of that function is also always smaller than the limit of the other function, right? Because if you think about it, right, if you have a diagram, and you have these two functions, right? Let's say this is gx, and this is fx, right? Actually, let it make wiggle a bit more. It's quite clear that if one function is always more than the other function, or at most equal, then no matter what point you pick, the trend of f is going to be smaller than the trend of g, right? Graphically, it has to be true. If one function is always smaller than the other function, then the trend is also smaller than the trend of the other function, no matter what point you pick. So that's something that has to be true if you think about it graphically. And with this property, there is an even more advanced theorem. The more advanced theorem is called the squeeze theorem, or the sandwich theorem, which says that if you have three functions, f is smaller than g is smaller than h, right? Smaller or equal, that is. If f is smaller or equal to g and g is smaller than or equal to h, when x is near a, and that somehow the limit of f and h are the same, then the limit of g is also the same. Once again, it's more easier to see graphically what it means. Right? So let's say you have three functions this time. Right? You have three functions. You have this time around, let's just say we have what color should I use? Let's use green, red, and blue, right? Okay, so blue, right? So this is h, right? Okay, this is h. This is f, and as you can see, the trend is the same around a point A, right? These two functions are both trending towards a particular value at A, which is called O. Okay? O. Now, if you have a function g that is sandwiched between these two functions, or squeezed between these two functions, then it's quite clear the function g also has to trend towards O as x approach A, right? Why is this so? Graphically, it has to be the case. As you can see, if h and f somehow touches each other, around A, then G being squeezed between them has to also approach the same value O. Why is this useful? This is useful because what happens is very often you have a very hard to a function G that's too hard to analyze analytically. G could be very weirdly behaving, and it's not possible to study it analytically. But you do know that it's always smaller than two easy to study functions. And you also know that two easier to study functions would be the same, take on the same value at a particular point. Then you can deduce the limit of the hard to study G function. Right. In mathematics, very often what you need is tricks after tricks to study something, because a lot of functions are simply too difficult to study directly. And this is one of the very useful tricks to study what happens to a function that is very hard to study, but is sandwiched or squeezed by two easier to study functions. And that's called the squeeze theorem.